Okay, answers for page 20 from the S1 heat booklet. For number 1, you just have a look at your learning outcome notes for 4 and 5. It's pretty much just recall straight from that. The ones more interested in question 2. And remember, it's important that you show your working, so you should be looking for similar working to what I have here. So what do we know in this problem? Well, we know it's 100 grams, so we've got M. And we know it's aluminium, and it's melting, so we can go to the table and get the change of state constant for aluminium changing from a solid to a liquid. And we get the L, the change of state constant, is 395 joules per gram. And we're being asked how much heat energy, so we're being asked EH. Now I know this working is going to get quite repetitive, but that's the whole point, right? That you get used to it, it becomes a habit. So don't take shortcuts. So once you've established what you know and what you've been asked, then you're picking the formula. And we've got EH, so we'll leave that in. We know that M is 100, and we know that L is 395. So we get the answer 39,500 joules. You don't need that comma in there, I'm just doing it to make it easier to read. Okay, and very similar for B, C and D as well. So in B we're told the mass is 200 grams. We go and get the change of state constant for iron melting, which is 267. And we've been asked EH. So once again, substitute in, remember, write the formula as it's given, substitute in. And because what I'm working out is on the left hand side here, I don't need to do any rearranging. And I can just work out that value. Okay, actually I'll start underlining my answers so they stand out a wee bit. C, 50 grams of lead. ml EH equals 50 times 25 1,250 joules. Give me a second just to copy that if you're still doing, but you can pause the video now. I'll start a new one. And for D, look up the table again. And formula, the substitution. And once again, what we're working out is on the left hand side. So no rearranging needed. And that's our final answer for that question. Now number 3 is very similar. The only difference is it's about vaporising, but the physics is exactly the same. We use the same formula. So if we go and look at question A, we're told it's 10 grams and it's alcohol, and when we go to the change of state table, we get that for alcohol it's 1,120 joules per gram, and we're being asked EH. So this is your repetitive practice, so make sure you're repetitively working out in the way that I'm showing you, so showing all this working so that it's a habit. So when you get to an exam and it's not a repetitive practice, you're not doing these under a heading that says these are this type of question, you've got good problem solving techniques. And for glycerol, for part B, 830 joules per gram. And remember, you're always allowed to use a calculator in physics. You don't need to worry, right? All you've got to do is make sure you're showing you're working properly. Then you can put the actual calculations into your calculator. And then last one for water. EH equals question mark. The value is quite high for water, like 2,260, you see it's the highest in the table. For this particular mass of water we end up with quite a large number for the amount of energy involved. Okay, all of questions 2 and 3 you were working out EH, which was on the left hand side of the formula, so there was no rearranging needed. That's different in question 4, but we still approach it. We start in the exact same way. What do we know? What we're being asked? But in question 4 we're being told the value of EH. We've still got our table to get values of L. And we're being asked then what the mass would be. Sorry, I forgot to put in part A. So we still do the same sort of working. We start with the formula, and that's the way it'll appear in the front cover when you're doing an exam. And then we do our substitution. So I know that EH is 2000, so I don't just write EH. I don't know M, that's what I'm trying to work out. But I know what L is, so I substitute for that as well. So what I'm trying to work out here is on the left hand side, so I've got a wee bit more working to do. The first thing I'm going to do is swap sides to get M onto the left hand side. And now I want to get rid of this times 25 here. So I do that by dividing by 25. That will cancel out with a multiply by 25. But whatever I do to one side of a formula, I must do to the other. The left hand side, let's say, simplifies to M, and then you can get your calculator out and do the right hand side. And that gives you the answer, 80 grams. Similar sort of idea then for B and for C, but just try and get used to that you're working, and try and also get used to that idea of, well, is what I'm working out on the left or the right hand side, because that changes your approach. Once you've done the first 2 steps, it changes your approach. It doesn't change it at any point up to that. And once again, M is what you've been trying to work out. Substituting in, what we're trying to work out is on the left hand side, so swap round both sides. Doesn't matter what order you write a formula, so we're not doing anything fancy there. And now I'm getting rid of that times 334 because I just want what M is. So I have to do something to cancel out that times 334. Now what my calculator actually says is 2.99401198. To be honest, if you wrote all that out in first year, we wouldn't get too bothered. I imagine though most of you will try and round it off a wee bit. If you rounded it all the way to 3, that would still be acceptable. Okay, we'll worry more about rounding when we get further up the school. For now, we're just trying to get the ideas. And in the final one, we know EH is. Once again, we'll look up our table to get a value for L. And we're being asked M. Substitute in, so remember these first 2 steps are the same no matter whether you're trying to work out the left hand side or the right hand side. The formula's in the front cover of the exam copy that out. Substitute the numbers that you know, the numbers that you don't know leave as a letter, because if you put a question mark it's easy to lose track. And then you've got to think these next stages might be a wee bit different, because what we're trying to work out is on the right hand side. We really want it on the left. Swap both sides round and then get the m on its own. So to do that here I've got to do the opposite of times 2260, which is divide, and then once again get your calculator out and rounding off, and let's say don't worry about the rounding off, we wouldn't penalise that at this stage. I'm right at the bottom of my page so I can't actually underline that just now, but that's your answer for that one. Okay, question 5, if you got to it. If you look carefully, you can see that in general it takes more energy to vaporise, or evaporate would do, 1 gram of liquid than melt 1 gram of solid. And the reason when we discussed a wee bit and watched a video about what's actually happening is that when you turn something from a solid into a liquid, you're allowing the atoms to move around, you're weakening the bonds a bit so the atoms can move around each other, but you're not actually separating them out. Whereas when you change from a liquid to a gas, you're totally separating out the individual atoms, and that requires more energy. So it takes more energy to completely free the atoms when changing from a liquid to a gas than loosening the bonds when changing from a solid to a liquid. Number 6. So a nurse applies some alcohol spirit from a bottle at room temperature to the skin, and that cleans, but the liquid spirit evaporates, and what happens? We get a cooling effect on the skin. Which of these explanations is correct? So if we go back and check our learning outcomes from evaporation, right, the spirit gives out heat as it evaporates? No, because if you look at evaporation, it requires the material to absorb heat. So B is the correct answer. The spirit absorbs heat from the skin as it evaporates, and that's what causes the skin to feel cool. And then lastly, number 7, you've got a wee kind of mini interpretation, as we'd call it. Right, close reading, I think you now call it in English. Okay, so if we're just trying to find out a wee bit, okay, what is water vapour? Well, if you go down to the 5th line, we see the steam above boiling water is actually a mixture of water vapour, brackets, gas. So that's telling you that water vapour is a gas form of water. So water vapour, you sometimes see it as the gaseous, right, but I'll just go with the gas form of water. As you put E-O-U-S in the end, you get an adjective, gaseous. But right, why is it dangerous to breathe in steam? Well, we've got some of the ideas in this about the danger in putting your hand into steam comes because the water condenses onto the skin, the water vapour condenses onto the skin, which causes a steam burn. So it would be dangerous to breathe in steam because you could get a steam burn inside your lungs, and that wouldn't be good. So it is dangerous to breathe in steam can get a steam burn inside your lungs. So you're using some of the knowledge from the passage and a wee bit of problem solving, adapting the stuff in the passage about your skin into your lungs. When the water vapour condenses into the skin, it becomes a liquid. Does the water give out or absorb heat energy when this happens? So once again, back to your learning outcomes 4 and 5, and you get the condensation gives out heat energy, it emits heat energy. So water emits heat energy when condensing. Okay, can you explain why gas condensing in the skin gives such a bad burn? Well, you kind of get a double whammy from this, because you get the energy given out as it changes from the gas into a liquid, but then remember, it will change into a liquid at 100 degrees Celsius. There's no change in temperature during a change of state. So you've then got liquid water on your skin at 100 degrees Celsius. So you get the energy both from the change of state and from the change in temperature when it's cooling as a liquid. So the gas gives a bad burn because it emits energy to change state to water at 100 degrees Celsius, then emits energy, I'm running out of space here, to change temperature to the same temperature as your skin. So from 100 down to say 30 degrees your skin. Okay, if you just had water, you would only have that change in temperature. You wouldn't have the change in state and the change in temperature.